Thank you, and good evening once again. It's a pleasure to be back once more. It's not rocket science. Rocket science is hard, but as the subtitle tells you there, it's only hard because maths gets in the way. And I'm going to try and convince you this evening that you can deal with it as long as you sort of put the maths to one side.
What do you do? Well, I don't mean to boast, but I'm a brain surgeon.
Brain surgery? Not exactly rocket science.
Part of a much longer skit, but I didn't want to bore you with the full amount of it. So, I'm not talking about rocket technology. I'm not talking about how to build one of these things. So that would be a fantastic talk, and I'd love to go to a talk on that. But no, it's not how you build rockets. It's what you do with them, how you use them to get around the solar system. I'm going to be talking about what rockets do, a little bit about orbits, or quite a fair bit about orbits actually, different shapes of orbits, how we figured it out and what they mean, and how we get from A to B, how we use orbits to get from one place, i.e. the Earth, to other places, i.e. other planets in the solar system. And also, not only how we do a short hop, but how we do gravity assist to help us get to the outer solar system. And towards the end of the talk, I'll be talking about these mysterious Lagrange points. How can we understand Lagrange points without any maths? How can we understand that it's possible to park a spacecraft in the middle of nowhere out at a Lagrange point, such as, for instance, James Webb Space Telescope? So let's start with the first question. What do rockets do, or what does a rocket do? If you ask this to a member of the public, the answer is nearly always, well, it's to lift things up into space. Well, yes and sort of no. The primary role of a rocket is not necessarily to gain height. Remember, the International Space Station and the Hubble Space Telescope are not above the atmosphere. They are in the atmosphere. Okay, the air is fairly thin up there at 400, 500, 600 kilometers, but they're still inside the Earth's atmosphere. The idea of going into orbit or getting out of orbit into another orbit around another planet, what is absolutely crucial is not height above the ground, it's horizontal speed. It is the horizontal aspect that rockets are necessary for. Okay, yes, it's a good idea to get as high as possible in order to get where the air is thin. So yes, the Hubble Space Telescope and the space station are not in the vacuum of space, they're in the very tenuous upper atmosphere. But if we want that not to have too much of an effect on our orbits, we want to get as high as possible. But height is not necessary for orbit. Horizontal speed is absolutely necessary for orbit. This has been known for an awful long time. If you go back to Newton's Principia, he had this diagram of what if you put a cannon on top of a mountain and fire a cannonball horizontally. If you don't fire it fast enough, it comes back to Earth and lands at A or B. But if you fire it fast enough, then it can go into orbit, C or D. And in fact, if you fire it really fast, you might be able to escape Earth's gravity completely along the trajectory shown by E. So this need for horizontal velocity has been known for centuries, but it sometimes gets forgotten, mainly because you always see rockets go vertically upwards. So yes, initially, rockets take off vertically. But notice that it's not long before they tilt over. And that's not a mistake of perspective. It's not an accident. That is a genuine tilt of the rocket, because sooner or later, it's got to build up its horizontal speed. So it gets height simply to clear all of the objects on the ground, like the occasional things like mountains and things like that. Gets enough height, but then it starts to build up its horizontal velocity because it needs to get to orbital speed in order to stay in orbit, as indicated by Newton's little diagram a moment ago. If you don't even think about horizontal velocity, if you just say, I've got a rocket and it's going to go vertically up, well, what goes up will come down. So, for instance, Blue Origin, the New Shepard launch a little while ago, it launches vertically, it goes up, altitude somewhere around 100 kilometers or so, But once they switch the engines off, what happens? It comes vertically straight back down again because it doesn't go into orbit because it doesn't have horizontal speed. So that's just, as it were, a suborbital lob, which is what the Americans did before they went into orbit back in the early 60s. So let's have a think about orbits. We need to mention Kepler and Newton. Buzz Aldrin's name is there simply because Buzz Aldrin is one of those astronauts that seem to have an absolutely innate ability to understand orbits. Yes, he was a PhD, and his PhD was in orbital mechanics, but he seemed to be able to visualize how you get from A to B, even though the orbital mechanics can be quite complicated. So let's have a think about orbits. First, the definition, possibly not what you think. An orbit is the path of an object affected only by gravity. It doesn't necessarily mean a closed loop, doesn't necessarily mean a circle or an ellipse. It simply means the path of an object affected by gravity. So if a rocket's engine is firing, whatever the path of that rocket is, it's not an orbit, because an orbit is the path of an object once you switch all the engines off and only coast under gravity. So we're all used to the idea that planets orbit around the sun and moons orbit around planets. So we're used to that idea. And Kepler, of course, observed the planetary motion and figured out that planets orbit in ellipses, and Newton figured out why. So the observations were made by Kepler, and the explanation was provided by Newton. The universal law of gravitation said that if the force of gravity falls off as 1 over r squared, then Newton said the mathematics tells me that we must have orbits which are circles or ellipses, or indeed one of the so-called conic sections. If you take a cone and slice through it, you get one of the 4 conic sections. If you slice through a cone horizontally, you get a circle. Slice at a bit of an angle, you get an ellipse. Slice at an angle which is parallel to one of the sides of the cone, then you get a parabola, and if it's a larger angle, then you get a hyperbola. So there are 4 distinct mathematical shapes that you can get by slicing through a cone. These shapes, circle, ellipse, parabola, and hyperbola, perhaps you recognize that they're also the shapes that you can use for mirrors to focus light. We don't tend to use circles, we tend to use ellipses and parabolas, but all of them will focus, hyperbole as well. So all of these shapes will focus light. And why is that? Simply because the maths, the underlying maths, I should say, is the same. In other words, the maths of working out how objects orbit according to a central gravitating body and working out the maths of shapes that focus light, it turns out the maths is related, not identical, but it's related, and hence we end up with the same set of shapes. So planets tend to follow elliptical. If you want to take a circle as just being a limiting case of an ellipse, then basically planets follow elliptical orbits. If an object falls from a very distant point, for instance from the Oort cloud, let's say for the sake of argument a light year or so away from the sun, if an object falls from that distance and comes into the inner solar system, then we see that as a parabola. If you wish, you can think of a parabola as being the limiting case of an ellipse, which is infinitely stretched. So just like an ellipse, which if you squash the ellipse until its length and width are the same, you get a circle. So if you take an ellipse and stretch it so it's infinitely long, then you get a parabola. So they're both limiting cases of ellipses. So if an object falls in from the Oort cloud, it'll follow a parabolic trajectory. If an object enters the solar system at speed, then it's the curve outside the parabola. In other words, it's a hyperbolic orbit that an object would follow if it enters the solar system at speed, as opposed to simply falling from 0 speed in from a great distance like the Oort cloud. So in 2017, in 2017, this rock came into the solar system, and it came in at some speed, and as it passed the sun, we could follow it and track it, and it turns out it was a hyperbolic orbit. And not only that, its speed as it went past the sun, the perihelion speed, was fast enough that it was clear that it had escape velocity, so it was going to escape the solar system. So we deduce from that it must have entered the solar system at some speed, and indeed will exit at approximately the same speed. If we think about what's actually going on, what do we actually need? Let's assume that we're not going to deal with the maths. So in terms of hand waving, how can we understand the way orbital mechanics works? Well, there's only really, I would argue, one concept that takes you through all of orbital mechanics. And that concept is, if we think about two bodies orbiting the sun, for instance, let's just imagine they're two hypothetical planets. The green one is closer to the sun, so it's got a stronger pull of gravity from the sun, so it moves faster, and so its year is shorter. Yes, it's got a smaller distance to cover, but also it's moving faster. The red object, let's just run that again. The red object is further from the sun. The gravitational pull of the sun is weaker, so that object moves less quickly, and hence its period is longer. Yes, it's got further to go, but also it's moving more slowly. That concept, that the stronger the gravity, the faster the object, that is it as far as orbital mechanics is concerned. That's it as far as rocket science is concerned. That's the only concept that you need to get your head around. Everything else follows from that initial idea. We can see that, for instance, it's a rather busy animation, this one, but right close to the Earth, we have satellites like Hubble and ISS going round in about 90 minutes. Further out, we have the global positioning satellites, which are orbiting the Earth in about 12 hours, and right on the outside we have geostationary satellites. These are orbiting the Earth in 24 hours. The closer to the Earth, the faster they go. The further from the Earth, the slower they go. Exactly the same argument that we were using for planets going around the sun. It's rather embarrassing to admit that in terms of understanding how bodies behave when they're being gravitationally attracted to each other and moving under the influence of gravity, we can calculate how any two objects behave. The two-body problem is a soluble problem, but it's rather embarrassing to admit that we can't do it for three bodies. And of course, there's an awful lot of objects in the solar system. 8 planets, 300 moons, I don't know how many asteroids, and a few trillion icy particles in the Oort cloud, but we can't even handle 3, let alone that number. So we always have to make approximations. For instance, we might look at a particular example and say, well, this looks rather neat. That must be easy to solve. It's 3 objects moving around. But this particular simulation, when we run the simulation for a little bit longer, oh, it wasn't quite what we thought. Yeah, we didn't start in quite the right positions, and very quickly it starts to look totally chaotic. We can run simulations. We can step in small increments of time and say, what would happen if this object pulled that object? How much would it move? Let's step forward in time and move everything like chess pieces and then recalculate the gravitational forces. We can run simulations, but analytically, we can't figure out what would happen to that system by solving equations in the same way we can simply solve the equations for a two-body problem and work out that an object like the Earth at this distance from the sun will take 1 year to go round the sun. So the three-body problem still pains us, and everything has to be based on either approximation. If we think about the moon going around the Earth and the Earth going around the sun, if we want to calculate how the moon goes around the Earth, we temporarily forget that the Earth is going around the sun. And if we want to work out how the Earth is going around the sun, we temporarily forget that it's got a moon going around the Earth, because we cannot solve it completely correctly. We just have to make approximations. So, notwithstanding the fact that we have to make approximations, how do we get rockets to take us from one point in the solar system to another? For instance, we know that if we have a rocket with enough horizontal velocity, we can go into Earth orbit. So we can put up the Hubble Space Telescope or the ISS. But how, for instance, do we get from Earth to Mars, and how do we get to more remote planets? Here's an indication of how a mission back in 2018 went from Earth to Mars. We don't simply wait until Earth and Mars are as close as possible and then go hell for leather in a straight line between the two, hoping that that shortest distance between 2 points means that's the easiest one. No, the easiest way to get from Earth to Mars, or at least the one that uses the least fuel, which is what you normally want, is to go from Earth and arrive at Mars when Mars is on the other side of the solar system. It's a little bit counterintuitive, but that's the easiest way of getting there. So notice that we left Earth in the bottom right, and we've arrived at Mars in the top left on opposite sides of the sun. Notice also that our spacecraft, the pink blob in these animations, As it approaches Mars, notice that it arrives slightly ahead of Mars, and then Mars catches it up, which means our spacecraft is actually traveling more slowly than Mars. If we want to actually go into Mars orbit and stay there, we have to accelerate once we reach that particular point in the orbit. So if we, that's way too complicated. Let's just simplify that. Let's dim that down a bit and remind ourselves we're trying to get from an orbit where Earth is there into an orbit, and ultimately we want to arrive at Mars when Mars is on the opposite side of the Sun. This is the most fuel-efficient way of getting there. The orbit, it's a so-called transfer orbit to get from the orbit of Earth to the orbit of Mars. It's called a Hohmann transfer. You might have heard that name if any of you are fans of the Martian film. They used the Hohmann transfer, and that word kept cropping up when they were talking about how to get astronauts or supplies from the Earth to Mars. So let me just remove temporarily the Earth and Mars. So you can see the Hohmann transfer is an elliptical orbit where the closest point to the Sun matches the Earth-Sun distance, and the most distant part of the ellipse in terms of the aphelion distance to the Sun, that matches the Mars-Sun distance. And in order to get from the Earth orbit into this so-called Hohmann transfer, it looks very similar at Earth. The green line and the blue line are very similar, but we need to give it a little bit of a nudge. We need to give our rocket, our spacecraft, our astronauts, whatever it is we're sending to Mars, our rover, we need to accelerate it in order to get it onto the blue curve. And that means we fire some rocket engines to accelerate. Now, rocket scientists never bother worrying about acceleration. The only thing that matters is how much have you increased your speed. Doesn't really matter if you do it over 1 second or 10 seconds or 100 seconds. What matters is what is your delta V, what is your change in velocity, because that determines what orbit you're now on. If you're an astronaut, you will care about acceleration as to whether you gain that delta V very quickly or very slowly, because that's the amount of pressure you've got pushing you into your seat. But in terms of getting a rover to Mars, no, you just fire your rocket engine and you calculate how long you need to fire your rocket engine to give you a particular delta V. So once you've given your rocket, your spacecraft, that delta V, you're then on the blue curve and up you go to Mars. Remember what we saw in the previous little animation. On arriving at Mars, if you simply coast along this blue line, when you arrive close to Mars, Mars is actually going faster than you are. Remember, it was catching up the spacecraft. So if you want to actually accelerate in order to get to the same speed as Mars, you need another delta V when you get there, another kick, another rocket burn, which will increase your velocity to match that of Mars. So if you want to get from A to B, the golden rule is you need to fire your engines to start your transfer, and then you coast until you arrive, and then generally speaking, you'll need another rocket burn when you get there. Looking at this picture, you might say to yourself, well, that's actually quite convenient, because if you fly from Earth to Mars, and then for some reason you change your mind and decide not to land because there's a problem, all you have to do is to avoid that second burn, and you'll simply come back on the blue line, back to Earth orbit. Fantastic. Except Earth takes 1 year to go around the Sun. Mars takes a couple of years to go around the Sun. So the blue orbit, not surprisingly, has an orbital period of about 1.5 years. So if you left Earth, arrived at Mars but decide not to land and simply come back on the blue line, you come back to Earth orbit 1.5 years later. So where's the Earth? It's done 1 orbit and a half orbit. The Earth isn't there anymore. The Earth is now there. So you come back to Earth orbit and Earth isn't there anymore. So unfortunately, you can't easily get to Mars and get back again really quickly. That's one of the problems. You can only get from Mars back to Earth when they are in the right position. So it might take 8 months or so, 7 or 8 months to get to Mars, but you can't instantly come back on the 7 or 8 month journey. You have to wait a while. That's why missions to Mars are more like 2 years or more than 2 years. That's why it's a lot more difficult than simply going to the moon, which is a few days there, a few days back. Basically, if you go to the moon, get out, plant a flag, do the usual things, come home again, Earth is still where you left it. But in the case of going to Mars and back, no, it isn't, because of orbital mechanics. So that's something we have to bear in mind whenever we're planning missions to Mars. But what about other solar systems? Mars is easy because it's the next planet out. But it was realized in the 1960s, if you want to go beyond Mars, what if you wanted to go to Jupiter or Saturn or Uranus or Neptune or Pluto or anywhere out there? Back in the 1960s, it was realized that, well, actually, you can do it a little bit faster than brute force if you use a so-called gravity assist, sometimes called a flyby or a slingshot. And the idea is use the gravity of one planet to slingshot you on to another. So it can increase your speed. It means you don't have to have such a big rocket engine. You don't have to carry as much fuel. That means you've got a bigger scientific payload, a much more attractive idea. It still might take years to get there, but hopefully not as many years as if you did it the old-fashioned way. So how do gravity assists work? Well, basically what you're doing, given that you can't get something for nothing, is you're trading off the energy and momentum of the planet. The planet loses a little bit of momentum, a little bit of energy, and the spacecraft picks it up. Because of the huge mass difference between, for instance, Jupiter and your space probe of a couple of tons or something, that means that Jupiter hardly notices, and yet your spacecraft can get a quite significant kick of extra speed. So let's just think about how it actually works. If here on Earth you've got an object on the top of a hill and you roll it into a valley, as it rolls down the hill, it gains speed. I hope that's of no surprise to anybody here in the room. And it has a maximum speed at the bottom of the valley, and then it will slow down as it comes up the other side. And then maybe it'll reach the top of the next hill, which by miraculous chance happens to be the same height. I'm a physicist, so of course I'm ignoring friction and I'm ignoring air resistance. This is an ideal situation. But what is perhaps not realized, everybody appreciates you gain speed as you go down and then you lose it on the way up. But what you perhaps don't realize is that at the same height, you must have the same speed. It's got nothing to do with the shape of a hill. It doesn't matter how steep it is. It can be steeper on one side and shallower on the other. It can be bumpy, as long as we're ignoring friction, etc. If you end up at the same height coming out as you were going in, you must be at the same speed. It's a conservation of energy argument. So whatever you gain on the way down, you lose on the way up. So by that argument, you think, well, how can a gravity assist work? Because if you're gaining because you're falling into Jupiter's gravity well, surely you'll lose all of that when you come out of Jupiter's gravity well. So how do you actually gain anything? Good question. Glad you asked. So here we are doing a flyby of Jupiter. The closest point to Jupiter will be the maximum speed of the flyby, the maximum flyby speed. At some distance away, doesn't really matter, let's just say we're beyond the influence of Jupiter's gravity, we'll be coming in at some inward speed. And from what I've just said, from the arguments of falling into Jupiter's gravity well and then coming out the other side, if we think of a point at a similar distance coming out of Jupiter's gravity well, surely the outward speed must be the same as the inward speed, so we haven't actually gained anything. Here's the clever bit. The inward speed is the same as the outward speed as seen by Jupiter. In other words, Jupiter looks at the incoming object, looks at the outgoing object, and they seem to be coming in, going out at the same speed. But Jupiter is moving. Jupiter is going around the sun. Jupiter has its own speed around the sun. So if the inward and outward speed are the same relative to Jupiter, if we arrange it that we come in towards Jupiter broadside, as it were, and we leave Jupiter's influence traveling in the same direction as Jupiter, our speed gets added to Jupiter's speed around the sun, and hence we get an additional kick. And it can be quite substantial. For instance, it might be that we come in towards Jupiter at 10 kilometers a second, but it might be possible to leave Jupiter's influence at 25 kilometers a second, more than doubling our speed relative to the sun as we head off to the next planet that we want to explore. So, well worth the effort doing a gravity assist, because instead of taking a bigger rocket engine and lots of fuel and doing a burn, firing the rocket engine to try and accelerate from that speed to that speed. We just let gravity do the work. We let Jupiter do the work. As long as we get at the right place at the right time, of course, we have to make sure that we send our spacecraft in the right direction. So the calculations need to be very precise to make sure that our spacecraft arrives at Jupiter at just the right time, such that these angles work out. But it can be done. That was demonstrated back in the early 70s. One of the first was Pioneer 10. Pioneer 10 was sent from Earth to Jupiter, and watch what happens as it passes Jupiter. The pink suddenly accelerates, much higher speed, and notice its initial speed was heading off in the same direction that Jupiter was heading. Let's watch that again. Its speed is falling, falling, falling as it goes away from the sun, but as it approaches Jupiter, there's a sudden kick and a sudden change in direction, a dog leg there where it picks up this extra delta V from Jupiter. So Pioneer 10 was photographing Jupiter, but also proved the idea of a gravity assist. Pioneer 11, shortly after, did the same thing, but it used the gravity assist from Jupiter this time, taking pictures, but then using, look at that, the kick actually sends it to the other side of the solar system. So Saturn and Jupiter are in different sides of the solar system here, and the kick from Jupiter was enough to send it all the way to Saturn. Another kick, notice the dog leg there, as it reaches Saturn one more time. As it goes past Jupiter, the gravity assist sends it right over to the other side of the solar system, and then as it passes Saturn, it gets another kick. And of course, along the way, it was taking pictures of Jupiter, taking pictures of Saturn. It wasn't just to prove gravity assist, it was to explore these planets. But this was used in a few years later, in the 1977s, Voyager 1 and Voyager 2 were launched, and the same idea was applied, slightly better cameras in this case. So again, a gravity assist from Jupiter gives it an extra kick and sends it in the direction of Saturn. And the mission for Voyager 1 was get a close view of Titan, one of Saturn's moons. Notice it didn't have a gravity assist as it passed Saturn. Its mission was get a good picture of Titan, because Titan is really weird. It's a big moon. It's got an atmosphere. We want to see what's going on. So Voyager 1 took images of Jupiter, and then it was directed to fly as close as possible to Titan. And that sacrificed the fact they couldn't do both. They couldn't go past Titan and have a gravity assist on Saturn. But now that Voyager 1 has got some nice pictures of Titan, Voyager 2, which is following close behind it because they were launched only a few weeks apart, Voyager 2 doesn't need to go to Titan. So Voyager 2 is launched from Earth, gets a gravity assist from Jupiter, and now it can do a gravity assist from Saturn. Look at that dog leg. Now it's heading off to Uranus, another gravity assist, and then Neptune. So freed from the restriction that it had to look at Titan, it's now able to have gravity assists from essentially all of the planets. These tick marks, by the way, at the end here, are just showing us that it's not quite in the plane of the ecliptic. Notice that as it passes Neptune, again, no gravity assist. It was not necessary to have a gravity assist to send Voyager 2 out of the solar system. It was already traveling fast enough, but these ticks tell us that it's actually diving below the plane of the ecliptic. That's because as it went past Neptune, rather than trying to get a gravity assist to go faster, it deliberately flew over the pole of Neptune in order to get the best possible shot of one of its moons, Triton. So again, the idea of a gravity assist was foregone in order to get the best possible picture of a moon. It's already going plenty fast enough to leave the solar system. It doesn't need a gravity assist from Neptune to do that. We can see that if we look at the speeds. Here is the speed of Voyager 2 as a function of its distance from the Sun in astronomical units, 1 AU being the distance from the Earth to the Sun. So here's the speed in kilometers per second relative to the Sun, and Earth is in the top left-hand corner, and when an object is sent from Earth out into the solar system, the first thing that happens is its speed decreases because it's flying away from the Sun. It's effectively fighting gravity. But notice what happens when it passes Jupiter. It gets a kick. Passes Saturn, gets a kick. Uranus and Neptune. Notice that the Neptune kick, it does indeed accelerate as it falls into Neptune's gravity well, but notice that when it comes out of Neptune's gravity well, it's actually just a little bit lower than when it came in. Remember, it sacrificed the idea of doing a gravity assist in order to look at Triton. But it's still plenty fast enough, because if we look at how fast do you need to go in order to leave the solar system, the escape velocity, that's the blue line. So as the spacecraft approach Jupiter, the red line is below the blue line. As the spacecraft approaches Jupiter, it's not going fast enough to leave the solar system. If it didn't get a gravity assist, it would eventually fall back towards the sun, fall back towards Earth orbit. But notice Jupiter, because it's a huge planet with a large mass, gives it an enormous velocity kick there. And then the velocity again falls as the spacecraft travels outwards towards Saturn, again still climbing out of the sun's gravity well. Then it gets a kick from Saturn and again from Uranus. So as soon as it's gone past Jupiter, as soon as it's got its gravity assist there, then it's already going fast enough to leave the solar system. Once it's above the blue line, it will be leaving the solar system. And regardless of whether it goes up or down thereafter, these objects, Pioneer 10, 11, Voyager 1, Voyager 2, have all been given enough of a kick from Jupiter to go fast enough to leave the solar system. Now, using gravity assist to cover these enormous distances when we get beyond Jupiter, Jupiter to Saturn to Uranus to Neptune and beyond, etc., it makes a lot of sense to use the gravity of these massive planets in order to go faster, in order to explore more of the outer solar system. But it's a little bit counterintuitive that actually it's been used to explore the inner solar system as well. Bepi-Colombo, for instance. Gravity assists can help to go to the inner planets by slowing you down. A flyby can be used to lose speed just as effectively as it can to gain speed. You just have to get the trajectory right. In the case of Bepi-Colombo, it left the Earth and then it flew past the Earth and got a gravity assist from the Earth. And the gravity assist in this case slowed it down. Because if you simply drop into the inner solar system to explore Mercury, you'd be going far too fast when you got there. And so you need to be able to slow down. So actually it had a gravity assist from the Earth. And then, let me run that simulation again because it's quite a nice one. After a gravity assist from the Earth, it then flew past Venus and got another gravity assist to slow it down. Having got a gravity assist by Venus slowing it down, what did it do? Well, it went past Venus a second time and had another gravity assist, which slowed it down even further. And that slowed it down enough to actually drop into the close to the orbit of Mercury, and then it did a flyby of Mercury. The flyby of Mercury was back here in 2021, but notice Bepi-Colombo 2018 to 2025. It's already flown past Mercury, but it isn't there yet. In other words, it's flown past Mercury to lose speed, but it's not actually going to go into orbit around Mercury in 2025. It's got to go past Mercury again and lose a bit more speed, and then go past Mercury again and lose a little more speed. And eventually, it'll be going slow enough that it can go into orbit and start studying Mercury. So the idea of doing gravity assists, flybys, slingshots, call them what you will, in order to lose energy is not quite so obvious, but it is now an accepted way of getting there, not necessarily as quickly as possible, but certainly as efficiently as possible, because you need very little fuel. You don't have to fire rocket engines to slow down. You use the planets to slow down until you're at the right speed. So basically, the bottom line is a flyby can accelerate or decelerate depending on what geometry, where you decide, are you going to arrive just ahead of the planet or just behind the planet? But in both cases, you save fuel, and that's the purpose of gravity assists. Saving fuel is always a good idea because when you get to your final destination, for instance, Cassini arriving at Saturn, it might be that you want to use your fuel deliberately to change your orbit. Once you're there and in orbit around Saturn, you're not happy with just having one orbit and taking pictures of the planet and the rings and the moons from a given distance. You want to keep changing your orbit to get different perspectives and to visit different moons. So Cassini actually kept changing its orbit over the periods of 2004 to 2017. It was continually readjusting its orbit in order to get closer to the rings or get this angle or visit this moon, etc. And it needed fuel to do that. So if you don't waste any fuel getting there, you've got more fuel for doing maneuvers to give you just the images that you want. So the final section, Lagrange points. I said that orbital mechanics, rocket science arguably, is simple. It's only the maths that's complicated. So can we understand how you can park in the middle of nowhere just from what I've said so far? Remember, I'll go through this one more time. Normally we would say if an object is closer to the sun, it feels a stronger gravitational pull, and if it's a stronger gravitational pull, it goes faster. The red object is further from the sun, a weaker gravitational pull, so it doesn't travel as fast. That is, if you like, the golden rule of orbital mechanics. So these arrows here are sort of representing the pull on the red object and the green object. The red object is further from the sun, so it has a smaller arrow. It is being pulled towards the sun, but with a smaller force than the green object. At a greater distance, the force is less, and hence it moves more slowly. Question, is that always the case? Well, we certainly can't change the gravitational pull of the sun, no, but we can arrange it such that the positions of these two objects are such that the red object, whatever that object is, feels an additional force. In other words, hypothetically, what if the green object was the Earth and the red object, not Mars, the red object is an object in an orbit slightly outside the orbit of the Earth. So we know that the Earth has a period of 1 year, so the red object is further away from the sun, so you might expect it to take much longer than a year, or at least longer than a year to go round the sun. More than a year by an amount that depends on exactly where it's sitting. But what if? What if the red object was actually close enough to the Earth that not only was it attracted to the sun, but it was attracted to the Earth as well? In other words, it feels the gravitational pull of the sun and the gravitational pull of the Earth. It is possible to find a point in space, in other words, a distance the size of the red orbit. There is a red orbit which is just the right distance so that when you calculate the pull of the sun and the extra pull of the Earth, the extra gravitation makes it move faster. So instead of taking more than a year to go round the sun, it takes precisely a year to go round the sun. So the red object goes round with the green object, goes round with the Earth. It doesn't go round more slowly, which is what you would expect. The extra pull of the Earth means that the red object is orbiting in exactly a year, the same as the Earth. So as seen from the Earth, let's run that animation once again. As seen from the Earth, the red object is always on the other side of the sun. As seen by the red object, the Earth and the sun are always in the same direction, always pulling together. So remember, as seen by the Earth, the sun side is what we would call noon, regardless of which particular time zone you're in. So the side of the Earth facing the sun is noon. The side of the Earth facing out into space is midnight. So that red dot is basically floating above midnight. That's how Lagrange points work, because what I've just described is effectively Lagrange point 2. An object sitting at Lagrange point 2 feels the pull of the sun, and it feels the pull of the Earth, and because it feels more than just the pull of the sun, it doesn't take a year and a bit to go around the sun, it takes precisely a year to go around the sun, so L2 goes round with the Earth. As far as the Earth is concerned, it's a static point in space, sitting there above midnight. This, of course, is not to scale. The distance from the Earth to the sun is 1 astronomical unit, and it turns out that when you do the calculations, the distance from the L2 Lagrange point to the Earth is about 1% of that. So about 1 million miles, give or take, given that it's 93 million miles to the sun. It's about 1 million miles from the Earth to L2. The idea is conceptually the same for Lagrange point 1, except Lagrange point 1 happens to be inside the orbit of the Earth. An object that's orbiting close to the sun, you would think, well, it's feeling a stronger pull than the Earth is, therefore it ought to go round the sun in less than a year. But L1 is sitting there being tugged by the sun in one direction and the Earth in the opposite direction, so it feels overall a slightly lower gravitational pull. So instead of going round the sun in less than a year, it goes round the sun in precisely 1 year. And so L1 is another parking spot that is always moving with the Earth. L1 is always between the Earth and the sun as the Earth rotates. So that's a good place to put a spacecraft to observe the sun. The distance, approximately the same. It's about 1 million miles above noon. It's 1 million miles above the surface of the Earth towards the sun. It's a good place to actually place an orbiting craft that you want to do solar observing with. If you want to see the sun, you're guaranteed the Earth will never get in the way. If you're sitting at L1, the sun is one way and the Earth is the other way, and they are always in those relative positions. They never change. And therefore, you've got an unobstructed view of the sun, regardless of what the Earth wants to do. So the principle is exactly what I've been saying. Stronger gravity moves faster. That's it. That explains all Lagrange points. If you want to work out where they are, how do you work out that they happen to be 1 million miles away from Earth? Well, all you have to do is to solve the equation where capital M is the mass of the sun, small m is the mass of the Earth, big R is the distance from the sun to the Earth, and little r is the distance you're trying to calculate. Just solve for r. Simple. Yeah, okay, yeah, I did say at the start that it's not that hard if you just skip the maths. So we're not going to do the maths, but basically that's it. I mean, that is just Newton. It doesn't look like it perhaps, but that's just Newton understanding that gravitational pull goes as 1 over the distance squared and depends on the two masses. If you juggle that around, you get the equations, and Lagrange worked this out ages ago. I can't remember when he worked out the Lagrange points, and Euler worked before him. But in principle, you can just throw these into a spreadsheet and you can work out where these things come. It turns out that L2 and L1 are 1 million miles away from Earth. Again, I'm not going to discuss this, but there's another Lagrange point on the opposite side of the sun called L3. Some people believe there's another Earth sitting over there because we can't see it because it's on the other side of the sun. There's plenty of science fiction films that use this so-called counter-Earth hypothesis. And there's a couple of other parking spots called Lagrange 4 and 5. In the case of Jupiter's orbit, that's where some Trojan asteroids tend to collect. But we're most interested these days in what's going on at L2, because that's been in the news in past years, because spacecraft have been parked at L2. If you put a spacecraft there, and if you have a sun shield, that sun shield can not only protect you from the sun, it'll also protect you from the Earth and the Moon as well, because they're all in the same direction, or at least approximately the same direction. So that's why Gaia and the James Webb Space Telescope have been put out there. You can see space without Earth ever getting in the way. In other words, you can look out into space, and the Earth's behind you, and the Moon's behind you, and the Sun's behind you, and the sun shield will protect you from whatever light or heat is being generated from those particular places. Now, technically, L2 is a point that's actually in Earth's shadow. When you work out that the Moon's shadow, of course, will touch the Earth when we have a solar eclipse, a total eclipse of the sun. The Earth is 4 times bigger, so its shadow goes 4 times further into space. So instead of going 250,000 miles out into space, the Earth's shadow goes about 1 million miles out into space. So actually, L2 is just about at the tip of the Earth's shadow. If you were to sit at L2 and look back at the Earth, it would be essentially an annular eclipse. The Earth would just about block out the disk of the sun. And of course, some of the sunlight would come through the Earth's atmosphere. So it's not a good idea if you've got solar panels and you want to charge them, it's not a good idea to sit in the Earth's shadow. But more importantly, it's not a good idea to sit at L2 because you would be in a direct line of sight between the Earth and the sun. And if you wanted to send radio signals to the Earth or receive radio signals from the Earth, there's an enormous ball of gas behind it radiating an awful lot of radio interference. So it would be very difficult to pick up signals from the Earth or send signals. Sending signals not so bad, but receiving them from the Earth where you've got the sun behind the Earth would be a problem. And of course, eventually, if you want to send more than one spacecraft out towards the L2 point, they can't all sit at the same point. Gaia got there first. Well, actually, Herschel got there first, but then Gaia's sitting there. So James Webb Space Telescope, etc. You can't have a car crash of all of these spacecraft at this one point in space. So they're actually all making smallish, they're actually quite large orbits around L2. If a spacecraft moves away from L2, the Earth's gravity pulls it back again, as indicated by these green arrows. There's a sort of restoring force, if you like. If it were drifting down in the sense of down on this slide, the Earth's gravity would pull it back again. If it drifted up, the Earth's gravity would pull it back again. However, if it drifted in the other directions, what if it drifted away from the Earth or drifted towards the Earth? Unfortunately, that's a problem, because if left to their own devices, an object that drifted towards the Earth would continue drifting towards the Earth. And any object drifting away from the Earth would continue to drift away from the Earth, as seen by L2. So you do have to worry about those two directions, towards and away from the Earth. And one of the ways of visualizing this is a rather colorful way of visualizing the dynamics of how are we going to work out whether or not we can park in this particular location. This is a sort of, you can think of it either as a physicist and say it's a map of the energy of the particle or the spacecraft as it goes around the sun, or you can say, no, let's just think of it as this donut being a hill, and these contours are height, and we're interested in whether or not an object rolls downhill or not. In other words, if you think of this where red is high and blue is low, we're interested, if you put a little ball bearing on this surface, would it roll downhill, and which direction is downhill? So let's have a look a little more detail about what's going on around the L2 point and think about which way is downhill on this particular donut, if you like. So let's just blow that region up so we can see it a little more clearly. These are contours of height. So this is a high hill in the bottom left-hand corner. It's a high hill in the top left-hand corner. And blue is a low point. And there's the L2 point as the red dot. So which way is downhill as seen from the L2? So you can see downhill is not in all directions. Uphill is not in all directions. Two directions are down, going left and right in this particular diagram, but you can see the arrows are reversed for the ones on the top and the bottom. So we're going from high to low, and going from high to low. So the arrows are always pointing downhill, but they're not pointing in all directions away from L2. L2 is not a hilltop as far as this surface is concerned. L2 is not a well as far as this is concerned, because we've got the directions different. L2 is a saddle. Now, mathematicians love saddle points. That's what they look like. A saddle point is called a saddle point because it looks like a saddle. You can see from the saddle on the right-hand side there, if you move in one direction, you go up the saddle. In the other direction, you go up the saddle. But if you go sideways, you fall off the saddle. So it's different depending on which direction you go. If there's only one take-home message from this talk, it's that the James Webb Space Telescope and Gaia are sitting on a Pringle, because Pringles are very nice manifestations of saddles. Some supermarkets sell faux Pringles that are not real Pringles, and they don't have the right curvature. Some of them are flat in one direction and curved in the other. That's not a Pringle. Pringles must be curved one way in the negative sense and the other way in the positive sense. So you can either ride up the saddle or you can fall off the saddle depending on which direction you're going. In this diagram with the red arrows, if you go up or down, the Earth pulls you back to where you should be. But if you go towards the Earth, if you drift towards the Earth, that's a problem. So when James Webb Space Telescope and other satellites, which are making small orbital loops or so-called halo orbits around the L2 point, they will stay in that orbit quite happily because Earth is keeping them in that orbit. But if that orbit slowly starts to drift towards the Earth, it needs a nudge to push it back again. And it can only do it in one direction in the case of the James Webb. If you think about it, if it drifts towards the Earth, they can quite happily let it drift for a few months and it will go a short distance towards the Earth. Then they fire their retros just to nudge it back towards the L2 point. But what would happen if it went beyond the L2 point and started drifting away from the Earth. It hasn't got any retros on the telescope side. It's got retros on the underneath of the sun shield, which gets hot. The telescope, remember, is cold. They want that to be as cold as possible because it's an infrared telescope and they want to keep all of the temperatures as low as possible. If they had thrusters on that side of the sun shield, they would contaminate the mirror and they would warm up the electronics. So they haven't got any thrusters on that side. So it's a one-way ticket. So they've deliberately parked it just this side of L2. So it drifts towards the Earth, they nudge it back. It drifts towards the Earth, they nudge it back. Very carefully, making sure they don't nudge it too far, because if they nudge it too far, it's lost forever. And that's one of the amazing things about orbital mechanics. Yes, it needs maths to get it right. And the precision with which they placed the James Webb Space Telescope at just the right point to allow that to happen without wasting any fuel was pretty amazing. By not wasting fuel, it means that because they can do this nudge every few months, if you've got more fuel, that means more months that you can keep doing this nudge. In other words, it's more operational time. Instead of just enough fuel to last 5 years, they reckon they've got enough fuel to last 10, 15, 20 years because they saved so much fuel by the precision with which they got there in the first place. So a fantastic feat of achievement. Some orbits are really weird, and this is why rocket science gets such a sort of reputation as being, it's impossible. Because, for instance, these contours that I showed you on this donut, these contours of constant energy are effectively racetracks for particles, racetracks for objects. So you can get an object moving in an orbit that looks like that, and that just looks wrong on so many levels. But that actually obeys the rules. It looks really weird, but remember, we're actually dealing with a system in which all of this is rotating. The Earth is going around the sun, and if we work out what's happening to this object and see which way round it's actually moving, it's going round this horseshoe orbit, as it's called. But if we think about the rules, it actually does obey the rules. When the object is closer to the sun on the inside track, it's closer to the sun, so it's feeling a stronger gravitational pull, so it's moving faster than the Earth. The Earth is going round in this diagram. Imagine it's going round anti-clockwise. So if it's going round anti-clockwise, this object is going faster, and hence it moves on that red line on the inside there. As it gets pulled towards the Earth gives it a little tug, and it now becomes at a distance greater than the Earth's distance from the sun. If it's further from the sun than the Earth, then it's a weaker gravitational pull. It doesn't travel around the sun quite as fast. It starts to fall back from the Earth. Remember, all of these are rotating in an anti-clockwise sense. So it tends to fall back, and eventually it gets tugged by the Earth and pulled closer to the sun, at which point it's moving faster than the Earth, and it goes back to this one again. Back and forth around this horseshoe. It sounds a bit ridiculous, but there are actually objects in these orbits. This is not just a mathematical curiosity. Objects have been found, not only in various planets, but in, for instance, the rings of Saturn. There are objects that are doing this. Some moons actually swap over as they get close to each other because their orbits are close enough that they start to feel each other's gravity, and that you can get these crossovers and these rather weird horseshoes. So it does actually obey the rules. The rule I stated, the one rule that you need to understand for all orbital mechanics, still applies to this. There are some things that just don't seem to make any sense whatsoever. Remember, I said right at the beginning, an orbit is just a path of an object under the influence of gravity. Doesn't have to be a circle, doesn't have to be an ellipse, doesn't have to be a parabola or a hyperbola. You can have loops that are not closed. So here, a mathematician has set up very carefully what if I had three objects, let's say they're the same mass, red, green, and blue, and I place them in these positions and then I let them go. Under the influence of gravity, what would happen? Now, we know what would happen initially. The red is going to be pulled towards the blue and the green, so it's going to move in the sort of top right sense. Blue is going to be attracted towards the red and the green, so it's going to move downwards, presumably. What's going to happen to green? It's going to move towards the red and the blue, perhaps a little bit closer to blue because it's nearer to blue. So the green is going to move towards the left, perhaps the upper left. So we know roughly what's going to happen, but the details are quite surprising when you find out what they actually do. This is the orbit, and then they slow down and stop, and then they fall back along exactly the same paths again. So, not circles, not ellipses, not parabola. Those are genuine orbits of three objects that started in those positions. Is it possible to actually ever get a three-body system that does that? No, we don't know of any way that can happen. The only way that can happen is if you start with three objects of a given mass and place them precisely at these locations with no velocity and then let go. And stars aren't born that way. Planets aren't born that way. Planetary systems and star systems generally are born out of clouds that are slowly rotating. So this is a mathematical curiosity. It is allowed by the laws of orbital mechanics, it's allowed by the laws of physics, but we don't know of any natural way that it could actually happen. But it's quite fascinating to realize that objects can move through space without actually completing closed loops. And don't get me started on black holes, because whenever you think about something going around a black hole, space and time around a black hole are so ridiculously warped that Newtonian physics simply does not apply. Circles, ellipses, they just go out of the window completely. We don't get anything close to what we would recognize as conic sections because of the extreme situations around black holes. So let me summarize by saying, why is rocket science considered to be so hard? Well, yes, there are definitely objects in the solar system that move in ways that are not, at first sight, intuitive. Some moons move around planets in ways that are initially quite surprising. Sometimes we look at particles in Saturn's ring system, and they seem to be behaving very oddly. But the bottom line is, it's always just the influence of gravity. Yes, the details, calculating how to put the James Webb Space Telescope at precisely the right location so that it goes into orbit around L2 and saves all of that fuel. Yes, that was not a trivial task, especially considering the phenomenal accuracy that they ended up achieving back when it was launched Christmas Day 2021 and then placed into orbit in early 2022. But the underlying concepts, even though the details, even though you've got to admire the people who do the calculations, the underlying concepts are within the grasp of everybody. Stronger gravitational pull leads to faster motion. The Earth goes round the sun faster than Mars goes round the sun. We all know that. That's really all there is to it. The rest is just maths. After all, it's not rocket science. Thank you all very much.